think we're on time. Let's get it started.
Okay.
Okay, give me a sec. Is that recording?
Oh.
We haven't published it yet, but I keep recording. Right. Okay, hello everyone. Welcome to our another episode of FSI Seminar Series. Today we have Dr. Adrienne from Department of Physics in the University of Central Florida. She's a planetary scientist and associate professor there. And to tell a little bit more about our presenter today, she received her BS in physics from University of Missouri and her PhD in astrophysical and planetary science from University of Colorado Boulder. Her main research interests are in dust charging and dynamics on planetary surfaces and plasma interactions with planetary and spacecraft surfaces. Since is teaching as well as the outreach events and is a co-host on the Walkabout the Galaxy podcast. I'm really excited to hear more about your research and experience. Please take it away.
Thanks, Doctor. I didn't put in anything from the project we're working on together because I figured you and Phil could cover that. I was thinking about that just now. Hi, everyone. I think I know a lot of the folks here, but it's nice to see some people that I don't think I've met, and it's nice to see the people I do know. So I am going to talk today a little bit about different ways to do experiments. So one of the thing, a lot of what my research is centered around is doing experiments that are applicable for the moon, asteroids, low gravity planetary surfaces. And so I do experiments that try to leverage reduced gravity platforms and reduced gravity environments. So I'm going to talk a little bit about that, just as partly as an informational thing, partly as a way to think about other things you might be interested in, but also in like partially wearing my hat of advocating for suborbital and research in that domain, which I'm happy to talk more about. And then I'm just going to highlight a couple of the projects that are ongoing right now. And I'm happy, hopefully I'll go through it relatively quickly and we can have some time for a little bit of conversation about those or questions at the end. And feel free to ask questions as we go. So let's see. Trying to think if there's anything on the slide I want to talk about. I guess, so generally my research falls along the lines of understanding planetary surfaces. So looking at regolith, dust on planetary surfaces, and also charging interactions. So the plasma environment that all of these planetary surfaces are immersed in. That has extended to, I'm currently involved in a lunar mission. So we're building up some instruments to send to the lunar surface. That's involved in building hardware that goes on things like parabolic and suborbital flights, which I'll talk mostly about here, and CubeSat development. So I'm not going to talk much about that today, but this is an example of a CubeSat that we built here at UCF that was studying spacecraft charging. So charging on spacecraft surfaces. And that's a 2U CubeSat for reference. Okay. Yeah. So probably preaching to the choir in this room, but I have this slide in a lot of my talks. So if you're not familiar with regolith, just walk down the hall. But also, so it's the finest part of the lunar and asteroid surface, and the dust is the very finest part of that material. And most planetary surfaces that we're thinking of exploring are covered in these dusty planetary environments. And so that's one of the reasons that I'm interested in studying them. There's a lot of work that goes on here at FSI that's involved in a lot of different aspects of studying regolith, right? And in studying planetary surfaces. And so I'm going to talk a little bit about sort of the bits that I am involved in. A lot of this covers different areas of understanding planetary surfaces. So what we see on places like Itokawa, Ryugu are these small rubble pile bodies that are have different textures and different shapes, right? And those are built up over time by interactions of the planetary body with itself, interactions with other things in space, and they form and modify the surface. And so by understanding the surfaces, by understanding the structure beneath the surface, we can build up an understanding of those bodies. And so to do that, we have to understand how things change and how they evolve, and what we're seeing on the surface, how that represents its current state, its history, and potentially what it tells us about what's going on in the subsurface. There's a lot of different processes that we need to use to explain what we see on planetary surfaces. So both in the formation of regolith, but also in how it changes and evolves. This includes impacts. So most things in space, impacts, right, are really big. They have a really big impact. They have a big effect on what we see. And that includes cratering. That also includes really fine micrometeorite bombardment that gardens the surface and churns it up over time. We see things like landslides or mass motion on planetary surfaces that reshape features. We see the results of electrostatic motion. So this has to do with the fact that if you do have these, and I'll talk a little bit more about this, but if you do have these planetary bodies, they're immersed in the solar wind, the solar radiation. It's this plasma environment where you have a lot of different charging, different things that are charging the surface. And so that can cause potential differences on planetary surfaces. It can cause the grains themselves to have a charge. And so you can actually get motions of particles on planetary surfaces due to electrostatics. And that can potentially do things like fill in low-lying areas and create ponds. It can do things like coat materials that are down on a surface over time. So for instance, there's been some work done on like the lunar retroreflectors that have been on the surface for a really long time and understanding how much dust has maybe built up on those surfaces. There's also some thermal effects that can cause breakdown of rocks at different time scales. And so what I work on is sort of in the range of the first three. I don't do as much with the thermal effects, but they're important on the surfaces. But the various projects that I work on sort of fall into those lines of different scales of impacts, different types of sort of mass motion, and geotechnical properties are tied into sort of all of those. And then as well as electrostatic processes. Let's see. So we can look at different planetary surfaces and impacts. Sometimes they're natural, sometimes they're human caused impacts, right? So we have some really great, relatively recent examples of ways we've looked at small bodies, so small planetary surfaces with very low gravity. And we've interacted with those surfaces, right? And we've now brought back samples. So both Hayabusa and OSIRIS-REx missions to asteroids have recently brought back samples. But we also have these phenomenal videos of what happened when we interacted briefly with the surfaces. So this is an example of Hayabusa 2, which is the Japanese mission, touching down on the asteroid surface. You can see that the surface was pretty loose. It broke up very easily. Also, there is some confounding effects, like it's impacting into the surface, but it also has a little projectile that it sends that creates some of the giant amounts of ejecta that you see. But you can see all of this material very easily is liberated and very easily flows away from the body because it's such a low gravity body, right? It's very easy to lose all of that material. It's loosely held there and it's very easy to lose. Similar thing was seen in the OSIRIS-REx tag SAM touchdown. So this is the OSIRIS-REx sample head that's touching down on the surface, sort of honing in and then touching down. Here, there wasn't an impactor as much, but it did sort of settle, crush into the surface a little bit, and then it has retro rockets at the end that pushes it away. So you see a little bit of disturbance due to the actual head itself, and then the extra cloud of dust at the end is due to the retro rockets pushing it away. And one of those super exciting things about, I feel like it's never actually going to get there.
Yeah, it's like
it's looping in the wrong portion of the video. Anyway, we'll go to the results. So they just recently started revealing some of the results from the OSIRIS-REx mission. So this is very exciting, it's fresh news. The tag SAM sample head, so this is the sort of the bottom of it that touched the surface, roughly. It touched down, it got a huge amount of sample in the inside. It actually got so much that they had trouble closing the door. And so actually all of this stuff that we see here is sort of outside of the main sample container. So this is just extra stuff that they got that got into the collection mechanism, and then there was a sort of lid over this. So it's all this extra really interesting material that they were able to capture in addition to sort of the main sample that we got. So what are the interesting things about this regolith? So this is very dark material because it's from an asteroid. It's very carbonaceous. They've already started to do some analyses on these materials. It's very carbonaceous. When we think about like asteroids versus the moon, a lot of the differences come in sort of the mineralogy and also sort of the size fraction of what we see on the surface. It's very easy to lose the really fine grained stuff from very small bodies like the asteroids that we've seen. It's either lost into space or maybe it's gone down sort of lower in the surface. Whereas on the moon, we know it's covered with this really, really fine grained material that's built up in layers on the lunar surface. So that's one of the big differences we see. But if you look here, in addition to sort of the big chunks, you do see a lot of really fine material. It's hard to say how much of that was like fine when it was initially captured versus became fine when it was captured or in transit, right? It's gone through quite a dynamic environment since it was originally on just sitting there on the surface. So I'm sure they'll be doing analyses of that and like what this particle size distribution looks like compared to what we sort of saw on the surface. So that's a little bit of background. So we're interested in understanding dirt, regolith on the surface of planetary bodies, right? How do we do that? And what sort of what aspects of it do I try to tackle? So I try to do experiments that we can, so I do experiments, right? And so we try to reproduce relevant environments to understand this dust behavior or charged particle behavior on planetary surfaces. You can do this on the ground here on Earth in 1G and get some really great results. So we do a lot of experiments in vacuum chambers in a lab over in the physics building, but also there's a lab here doing some awesome stuff that's similar to some of this, where we put things in vacuum, right? And we try to understand how it behaves when you get rid of most of the effects of water, atmospheric drag, things like that. This is an example of a very old experiment. This is pre-Tyler. We were just talking about. This is a pretty old experiment looking at just simple spherical red beads in a container. You do an impact into those beads, you get ejecta, you look at the dynamics of that ejecta with different impact speeds, different impact energies, and you can make then predictions based on your known experiment conditions for what might happen if you do similar things in reduced gravity or with different planetary gravities and things like that. But a challenge to a lot of these experiments that we're interested in is that they happen in 1G on Earth. So you have to hit something pretty hard on Earth actually to get it to sort of lift up off the surface and do something interesting and dynamic. It doesn't seem like it because we're used to doing everything in 1G. But if you're interested in really gentle impacts, if you're interested in really small forces that are maybe having grains stick together, which have to do with how we look at the regolith and planetary surfaces. You actually need to go to places, you need to find ways to reduce the effects of gravity. So a lot of the things we look at, a lot of the things we look at are things like how do the grains stick together, right? And so that's informed by the grain properties, material properties, shape, size, things like that. And some of that you can look at with these ground-based tests, but some of that you need to disentangle from your behavior in 1G to be able to actually see really interesting dynamics. The other thing I mentioned earlier was that I study how things charge and how charged grains behave. A lot of that, the charging is important, but in 1G, the charging behavior is sometimes minimal compared to what we see the effects of gravity, right? So like if you're thinking about charging dust grains, like a great example to think about is computer screens or TV screens, right? You always have dust electrostatically clinging to the surfaces of those things. That's very, very fine dust. It's actually typically organics. It's not the dust I study, just rock, but very, very tiny rock, right? But that dust has a very different sort of like mass ratio, and so it can stick to the screen really well. So you can think about sort of those relative forces of what makes things stick to your screen versus fall and gravity And that's where we're trying to sort of reduce those forces. So one of the ways we can do that is by still doing experiments here on Earth, on the ground, is with drop towers. So there's a number of drop towers around the world. There's a few in the US at NASA Glenn Research Center. There's one up in Washington. There's one in our lab over in the Physical Sciences building. That's a picture of it right there. Ours is a 3/4 of a second drop tower. The one at Glenn is around 2 seconds, I think. So ours is about 3/4 of a second. We drop a payload from the ceiling to the floor, and in that time you have free fall, you have microgravity. And so we're able to do some pretty cool experiments actually in that amount of time. You use high speed video and you get at 500 frames per second, you get like 300 frames of interesting data, right? So we can do really short duration tests in the drop tower in the lab. And this is really great for being able to sort of test initial technologies, test initial science questions, where you're like, okay, I can think of an experiment that I can do in a short amount of time. I can test how I can build it, how I can develop some of the mechanisms in this experiment, and then potentially use those to progress to like higher fidelity or longer term or anything like that. So this is an example. So we've done a variety of types of experiments. This includes low velocity impacts, so very, very slow speed impacts. So like if you drop a marble from like an inch off the table, slower than that, right? So, and it actually creates big ejecta plumes when you're in microgravity. We also have been more recently doing a lot more with looking at plume effects on regolith. So this ties into if we're landing on planetary surfaces, engines are going to blow a lot of dirt and dust away from the lander, and it's going to modify the surface beneath you. How do we understand that? We do it with large scale tests, but we can also do it with pretty small scale tests in a vacuum microgravity environment. And so we've been doing some experiments with that here. And I'm not going to talk much about those today, but I can talk at length about them some other time or in questions. Here's a pretty example of a plume into a container of, I think these are just stainless steel beads. So this is in the drop tower. We have a side view and a top-down view looking at what the sort of ejecta looks like when you do a plume of air down into a container of regolith or simulated regolith.
How do you contain those at the initial drop so they don't just all go? Do you have a cover over it that you open up after you get to 0 G or something?
So in the drop tower, we don't have to do that because it, so when it drops, there's not too much of a kick, so you don't get it perturbed. So it just falls. The most of the regolith actually just falls with the chamber because there's no additional forces causing it to come up or anything like that. So we've done a few tests of like what the accelerations are when we drop it and things like that. And we've looked at over the course of time, a lot of experiments, and we don't see much perturbation of the surface when it does its first drop. You might, if you had like a much longer drop, you might be able to sort of see a perturbation over a longer amount of time, but we drop it and then we have a short period of time and then we send the plume in. So for the most part,
started testing with our Titan tower, and so I've been looking at this literally all day.
Oh yay. Are you seeing big perturbations when you do the first drop?
I see things that are interesting.
Sure. Okay.
You know, it's trying to understand what all those things are, and, you know, do they matter or not?
Yeah. Yeah, so we've instrumented with accelerometers like at different locations in the box. We've looked at if you have like spherical beads versus regolith. Like spherical beads are really great. Low density spherical beads are really great to see if you're going to get some perturbation because they move really easily, right? So like we've done a long time ago, we did some experiments with that, and we haven't generally so our experiments are released from the top from an electromagnet. So it just sort of releases pretty cleanly. And we haven't, I mean, occasionally when it gets out of whack, we see some issues, but we generally don't see issues due to it dropping.
Cool.
On our flight experiments, we always have covers that contain it before we do any sort of, and I'll talk about
dynamics.
Yes. Yeah. And on the parabolic airplane flights, everything's going everywhere. So, I mean, at the end, it's a giant mess when it hits the bottom. So. These aren't really resettable experiments, unfortunately. They are, It just takes a few minutes to reset once it hits the ground. And the nice thing about the drop tower is you can do pretty rapid experiments. It just depends on how hard it is to reset, how much of a mess you make.
I did
And-
75 today.
Oh, wow. But you're not pumping down to vacuum.
No.
Okay.
Thank God.
That's, yeah. I'll show this one really quick. So this is CI, like millimeter and larger chunks of CI in a plume experiment. I promise the left one is a video. And this is just with the experiment sitting on the bench top, so in 1G, and this is what happens in microgravity. So like, it makes a big difference. You can see that it's playing, there's like little fines that go at some point in it, so you can see that it's actually a video. Here's a more dramatic one. Again, you don't really see much in the 1G version, you see a poof of some of the smaller stuff getting thrown up. And then it's a giant mess. And this was just a longer duration plume, so it's a more energetic burst of air into the simulant. Okay, so stepping up from that, you can go to parabolic airplane flights. So these get you about 30 seconds of microgravity, which gives you more time, more than like a second, right, to be able to sort of look at either processes that take a longer amount of time, gather more data, test different technologies that you need something like more than 3/4 of a second to test, right? So for us, this means going to potentially lower impact speeds. It means doing things where we can look at interactions that happen more slowly, or that we need to look at how they evolve slightly over time. These plane flights give you the opportunity for that. And a lot of folks that do the parabolic airplane flights are doing huge ranges of different technology development, right? So people do human factors stuff a lot. So different wearable sensors, how do people react in microgravity, things like that. A lot of folks who are trying to understand things like fuel and liquid behavior for future spaceflight applications right now are flying on these flights, and many other things. It's also really great if you're a planetary scientist and trying to understand how things behave in different gravity environments, because the flights, they can give you Martian, lunar, and 0G. So reduced gravity in a few different ways. And so you can actually test how things behave slightly differently in those different gravitational vectors, usually in the same flight. I don't know, that's just, and you can do flips. I guess I added that one. Here's an example of an experiment called SLOPE that we were doing to try to understand slopes in microgravity. Just send this to Parks again. And so in different parabolas, we can look at both how steep of a slope you get with different material types. We've also looked at how much the material compresses as a function of going back into 1G and then into like 1.8G, which is sort of your peak when you're in the bottom of the airplane's trajectory. Sometimes you get weird things flying to the surface. This one, we did a little burst of air into the chamber also, so you can see it sort of circulating and making the beads go all over the place and then form a really interesting slope. This one was the airplane gave us negative G's, and they sort of bumped us up to the ceiling. So you can get some really interesting ways to study regolith behavior and different sort of geotechnical properties that way.
Curiosity, because I know nothing about that. So you use the same sample several times?
Yeah.
For different experiments?
We can, yeah. Yeah. So on the plane flights, we usually have 8 to 12 boxes, experiment boxes, and we can use them. Sometimes we just use one per parabola, like for impact experiments, we can usually just do it for a parabola and then you can't really reset it in between.
Yeah, because I'm just wondering if there is any change on the features of the sample, or the very small, I don't know.
Yeah.
You start to doing a lot of times.
Yeah. Yeah. So on the plane flights, you get 30 parabolas. So you get somewhere around 20 versions of the experiment, potentially, if you're rerunning the same box over and over again, maybe 30 if you're doing it really well. And in that time, we look at things like how fluffy it is, how compact it is. We can look at like particle size distributions. So we can look at all of that and like how that changes over the course of the flight. For the 30 parabolas, you don't get a lot of change in the sample. In some of the other experiments, or if we did more where we're blowing air, for instance, and like really disrupting them, you might see more breakdown and changes like that. Depends on sort of how hard you are on the samples, I think. Yeah.
Do you have to, so you have, your experiment and, you're you get to 0G in the parabola, and now you've got the experiment ready to go. Do you ever have to inertially stabilize the experiment or anything like that to try to not have any initial conditions that you do? Okay.
Yeah, so sometimes when we fly, so this experiment is mounted in a rack that's attached to the airplane.
Right.
And it is always mounted in the rack, so we always keep it, so it just experiences whatever the airplane is doing.
And whatever vibrations are in the airplane.
So there's some vibrations, there's like the correction maneuvers they're doing, then that's where you get some of these like negative G's.
Yeah.
We've done other experiments, where we free float the experiment boxes.
Right.
And those are clean, they're separated from the plane's,
Just in the air.
acceleration vectors,
Yeah.
and they're just in the air. So you do have to like have it pretty stable, you let it go, and then you do the experiment, right? And there is various levels of success when
That's
you do
what I
that.
was asking is, have you thought about, having some small reaction wheels or something like that to hold it in place, essentially
That would be really interesting.
nailing it in
Yeah,
inertial space.
yeah, you could, I mean, there are definitely people that do things with reaction wheels on parabolic flights
Yeah.
and test the performance. You could do something like that on this. It would be an interesting
It's in-
technology development.
It's curious to me if it would matter, right?
Yeah,
There's a lot of variables you're probably trying to control.
yeah.
To look at these little tiny.
Yeah,
things.
yeah, how much like rotation the box has naturally and things like that, yeah. I mean, there are things like that, I don't know if that level, I could think more about if that level of technology development would like help. Or how much time versus how much
Yeah.
time you have and things like that, because there are sometimes where we release it, it's very clearly not gonna work well, and you don't do the experiment on that parabola.
Right.
So like those flights, we usually only have like 8 boxes, and it takes us the full time still mostly, because you have a parabola that's like, oh, this is a bad parabola, or I didn't get a good release on that one, or
So
something.
it's all yield
Yeah,
essentially.
yeah, so it could be, I mean, if you wanna like double your output, maybe.
Yeah.
You could try something like that, and it'd be good technology testing, right? Like, it would be really interesting to see how that would affect the simulant
Yeah.
and things like that, so that's definitely could have applications for CubeSats. Or things on the moon or asteroids, so. Yeah. Okay, let's see. So moving on from parabolic flights, at least for now. Next sort of step up, both vertically and in time, is suborbital flights. So these are with companies like Virgin and Blue Origin, where you get around 3 minutes of microgravity. So you have about 3 minutes to do an experiment. Both of these also offer interesting opportunities to do high altitude observations. So folks like astronomers, upper atmospheric scientists are interested in these platforms as well, because they're starting to put sensors on the exterior of the vehicle, or have a telescope that can look through the window, for instance, right? And so you can do upper atmospheric studies, you can do minimal astronomy studies, but you can be up above 99% of the atmosphere, right? More than 99, there's some decimal points there too. So you can get a bunch more data, you can do longer experiments, you can do different technology testing. These platforms both have really clean microgravity also, so it's a really nice, like, so on the parabolic flights, to your question, sort of, especially when you're on the plane, you sort of get to like microgravity, but really it's sort of milligravity. You don't really ever get below like 10 to the -4 G's. It's pretty much milligravity at the best. With these, we've seen really clean, like 10 to the -5 probably gravity, and our dirt just stays there, right? So you can, that's the dirt doesn't lie. So you see really nice clean profiles when the mission works nominally. And so you can test a lot of cool technologies for that. And suborbital flights also offer opportunities to test like launch and landing technologies. So in addition to the flight projects, there are companies like Maston, now Astrobotic, Exos, that are doing sort of more tethered and ground-based tests, looking at plume effects and interactions with materials and technologies. So an example of a project we flew with Blue Origin on a suborbital flight with Strata. This is Dave. He's my mascot. He's been to space twice now, almost 3 times. Looking at particle behavior and asteroids. Oh, I think I have a little video for that too. This is an example of the experiment. You can kind of see little particles moving around when it opens. This is in the microgravity portion of the flight. I was trying to make an asteroid here, it didn't work. There was like a clump of material and 3D printed cups. We separated the cups, the material stuck to the cups, not to each other. So it worked, but not the way I wanted it to.
Did we ever try to measure it to see if the reason that they were, the blast shards moved up was any like electrostatic force or anything like that? Or did we?
I think it would be more atmospheric than electrostatic. Like these two tubes are at vacuum, but it's not the highest vacuum. So it's probably more of like a pressure difference that you could like a right when you do that. But it might be that they were sticking to it. We haven't, there's not really a great way to measure it. We could redo it and try to understand it a little bit better. Yeah. Okay, so going up from there is the International Space Station and upcoming commercial low Earth orbit destinations. So these are long-term destinations where you can put a payload and fly a payload. I'm not going to talk as much about that today, but it's obviously if you're interested in long duration platforms, these are really interesting. One of the interesting things about the commercial low Earth orbit, the CLDs, is that they are currently in development, right? So they're looking for what are people going to want to do in space long term. So they're like trying to figure out what platforms should we have available, whether they're external or internal, right? So if you're interested in ionosphere and upper atmosphere things from the space station, right? What kind of platforms would be available for that? What things might we need for microgravity experiments? What freezers do we need, right? They're all still in the development phase for that. So it's a really interesting time to be sort of providing input to those companies that are developing the follow-ups to the ISS.
Annie, are they seeking that input from you or are you offering it to them?
They have been systematically seeking input at meetings and certain from certain communities.
So
Yeah.
I mean, I imagine Sierra Space, since they want to build a space station, some of those companies are probably like
Yeah.
trying to do that kind of
Yeah.
marketing research.
Yeah. So most of them have been starting to talk to various communities, biological, physical sciences communities, other communities about like what those platforms look like.
Right.
In the recent decadal survey for biological and physical sciences in NASA, which includes like fluids and biology and I don't know, quantum gravity and things like that, right? Like those have specific, it now has specific language in it about sort of starting to develop capabilities for next generation space station type stuff.
Right.
And part of that was input from those companies and part of it is feedback to the companies. So like there's interest, there's people, and they've done a few surveys and there's definitely interest.
I mean, you got a company like Sierra Space who's trying to drive a
Mhm.
commercial business.
Mhm.
And I would have to believe they're smart,
Yeah,
that they're going to be
I hope so.
soliciting, inputs from you. And, I mean, I can imagine, if somebody wanted to go up there and play with regolith, they need to have an area where they can get dirty and clean it again. And,
Yeah,
you can imagine that you could make a mess of the space station pretty quick if you got an accident.
I can't imagine that. We've flown regolith payloads now on the ISS and it's a lot of safety.
Yeah, I'm sure.
Yeah, this is a video of one of our experiments that we worked on with folks at Johnson Space Center being installed on the station. And like, yeah, the levels of safety are intense, right, for all payloads. And if you're talking about A, pulling vacuum and B, putting dirt up there that could like escape into the air, they're not always super happy with you about that. But that is perfect, right? So like glove boxes are a thing on the ISS, but maybe you need something more than a glove box, right? Or a bigger glove box or a bigger workspace that has different cleanliness protocols. And like also testing how that applies to like when we're on the moon and dirt's everywhere and you can't get away from it. What do you need to do to clean things? And
Or
so
some kind of spinning thing that you can artificially generate gravity in it to collect everything and then.
Yeah.
Unspin it or some whatever.
Yeah. I
I'm
like
sure
it.
they're all over it.
CubeSats really quickly are also a super awesome orbital payload, long duration, very tiny, itty bitty living space, right? So very tiny payloads, but really cool for technology development, really interesting for Earth observations, solar observations, and now they're becoming more in the planetary realm as well. We are building up another radio tower on the physical sciences building so that we can potentially collaborate with radio astronomers, but also to do CubeSat development and CubeSat communications more successfully than we have in the past, which is not successful. Okay, let's see. I'm gonna go quickly through a couple of types of experiments that we've flown. So I like to talk about strata because it's one I'm working on. I'm working on one aspect of it, several aspects of it right now. It's sort of been a long duration project for my existence, my research. But so the strata family of experiments is strata is not an acronym, sort of uniquely for a lot of things. It's just short for we're trying to understand stratigraphy and layering of granular materials in reduced gravity environments. So how does having low gravity affect how materials layer and sort and segregate, right? And so we flew back in 2016 an experiment called Strata 1 on the International Space Station. This is pictures of it, an overhead view of when we got it ready for flight, and then this is on orbit. Camera views from our science cameras. So the strata family of experiments is looking at these different regolith dynamics. We've done a few different versions. We've flown on the ISS, and we sort of went backwards because we flew on the ISS first. This was in collaboration with folks at Johnson Space Center in the Ares department there, so the astromaterials research group. So they were very interested in asteroids, low gravity bodies, and looking at material dynamics. And so we worked with them to develop this sort of test payload. That ended up staying up on station longer than we expected, and we got a lot of really interesting data that we're still analyzing. We did some like spherical beads, we did glass shards that were broken up versions of the spherical beads, and we did actual crushed up meteorite, and then we did some simulants. And so we've looked at a lot of different iterations of this experiment that flew on the station. This first one was passive. It just sort of the tubes sat there in the gravity or lack thereof, right, on the space station for basically a year. And we watched what happened. And it turns out that even though it's a passive environment, even though you're up on the space station, that's a microgravity platform, the astronauts float around, right, you actually have a lot of accelerations and changes in the environment. So we had an accelerometer mounted on the face of the experiment. And we're now using that to understand, okay, what was our vibration environment? What were our acceleration profiles? What caused all of the regolith to move around like it did? Because we actually did see a lot of motion and a lot of sorting over time. And so this is some time lapses from early in the experiment, but you can see how the material moves and changes, and it's just sitting there. So the ISS vibration and things like that are causing it. I had an undergraduate student that worked for a while on this, and now a graduate student who's working on this, Kayla Shang, looking at the sphere and the shard tube, so the colored beads, because they're easier to see than the dark regolith. Turns out that's still really hard to analyze, and we're still working on that. But looking at sort of what that evolution looks like, and you can see the red, green, and blue particles represent different particle sizes, and so they move differently over time. And so this is just looking for over the whole year of the mission. So with time in like 8 different bins of that image, we just sort of binned different parts of the image. What did the particles do and how did they move around? So there's a lot here, but basically looking at how the sorting and changes occur, and like, did the big particles move more than the small particles? Things like that. We are also looking at how to do some of the analysis for the really dark simulant tubes. Requires a lot of image processing, and so that's very much in ongoing question.
Do you have access? NASA provides you with, you know, logs that detail when they do orbital corrections and that kind of stuff, so you could correlate it to the.
They didn't provide that, but we can get most of that information either from publicly available records or by emailing some folks and being like, hey, can you send us stuff about what happened on these days, kind of thing.
I'm sure even things like, you know, when certain machinery is running on board, it's probably putting vibrations into.
Yeah, so there's a big freezer pretty close to where our experiment was running, and that had some motors, and it was pretty noisy a few times. Yeah, we do have that accelerometer, so I also have had a student who's been working on pulling out, if we look at the different acceleration vectors as a function of time, what frequencies do we see peaks in? When do we see big accelerations and things like that? And trying to correlate those with when we see those spikes in the tube data. So this is all ongoing, although hopefully going to be a paper pretty soon. So maybe I'll be able to give a more full-fledged talk on it soon. And then let's see. So we also, I already showed that. I'm going to skip ahead. So another experiment that I have going is called ERIE. So we're changing sort of the physics that we're interested in for a minute here and going to regolith charging. And so I talked briefly about this earlier. So particles on planetary surfaces, insulators anywhere, right? When you move them around, when they're exposed to plasma, they're going to charge. When this can happen due to the incoming charged particle environment, can be due to photo emission, due to solar radiation. It can also be due to what's called tribocharging, or what happens when you rub things together, right? So when you rub your feet on the carpet, and you live in not Florida, and you touch something, you get a shock, right? It's really terrible giving this talk in Florida because it's like, what? No, you don't. That's fine, right? But so when you rub things together, it's called tribocharging. You exchange charge between the grains or between whatever surfaces they're in contact with. And that happens due to motion on the surface naturally. It's also going to be really important when we're having rovers driving around or astronauts walking around on the lunar surface, for instance. And so we're trying to understand that a little bit better as well. And so I have an experiment called ERIE, the electrostatic regolith interactions experiment, that is looking at this charging behavior. This is done in collaboration with folks at Kennedy Space Center who have been developing charge measurement sensors for the last decade-ish also. So we're trying to understand that. So this experiment is built on heritage from an experiment called Collide, that flew on the space shuttle. So Josh Colwell was the PI of these experiments. And it's the experiments we've been doing, looking at impacts into regolith for a long time now, a couple decades, I guess, technically. And modifying that to look at the charged particle behavior. So in these experiments, we typically do impacts into a tray of regolith, where that was the chamber. We have a bed of regolith down here and a door that slides open to reveal the regolith when we get to the microgravity portion of the flight. But from early, so from early experiments, we saw that, from early experiments, we saw that we were able to, here we go. When the tray door slid open, you started seeing these grains flying up and out of the chamber. Right, and this is not because of gravity. So this is not like, because this was on the space shuttle and it's like been up in space for a little while before this is all happening. So these grains are charging due to the door opening and rubbing them against each other and rubbing on them. And then they're repelling each other and sort of flying up into the volume because it's in a microgravity environment. So they just repel and go everywhere. So this is really old data. We sort of looked at it a few years ago and we're like, oh, hey, maybe we should actually study that. So we've been developing this experiment to fly on suborbital flights and look at how we can study the charged grain behavior, but also the charging of the regolith. So we're working with Kennedy, who have this history with developing some sensors to try to understand contact charging and tribocharging. Originally it was developed for a Mars rover and a Mars sort of scoop. It was then modified to be developed for a wheel that would go on the lunar surface. And so for these sensors, there's a number of like different patches of material that are different spacecraft relevant materials, but are different on the tribocharging scale. So when you rub them against each other, they're going to get very different charges. Or if you rub them against regolith, they're going to get very different charges. And so we've been updating the electronics for those sensors. And so we put these sensors in the underside of the door that's sliding open. So as it slides open, those little sensors rub on the regolith, and we can look at the charge that's put onto those plates. So we've been developing those sensors and testing them in this experiment. There's screenshot a little bit of how that works. So we have a circuit board sort of at the top of the door, these insulators that then poke down through and rub along the regolith. They're basically little capacitors, so we can measure how much charge builds up on them. This has had 1.5 flights, technically. So Erie has flown once. The first time we had an issue, a mechanical issue with the door only partially opening, which was really, really frustrating because we've flown those doors a number of times and not had issues. Anyway, so it partially opened, we sort of got data. Turns out the electrometer also had a little bit of issues still. So we fixed a bunch of that, and then we flew it again, and the rocket didn't go very high. And the capsule separated from the rocket though. Payload was fine, rocket went boom. But everything is okay, and we're gonna refly it again very soon, sometime, hopefully. This is us at the launch after the first flight was successful. But so we've done a bunch of testing of the electrometer and this regolith. These are some plots that are exciting to us, but probably nobody else. But basically we're looking at what happens when we are running our experiment. The thing I didn't mention before is that in addition to this door that slides open, we have 2 parallel plates on the side of the chamber, so that when the dust grains that are charged do fly up, if they have a charge on them, it'll change their motion because there's an electric field across them. So we'll be able to sort of understand a little bit better also how those grains are charging. So this is characterizing how much the plates were being affected by that high voltage potential we had in the chamber. And then this was doing a bunch of fun rubbing on different materials to measure how our sensors were charging up. So we could see that different materials were charging differently. We do have data from that second flight. I'm going to call it a flight asterisk. And that we could see some really interesting stuff actually when different events happened in the flight. So we were able to see that there was like some charging that started to happen due to the initial flight. And then we see some different behaviors and separations when we sort of see negative G's. So when the regolith flies up and sort of hits the sensors versus when we're in really strong downward G's and it separates from the sensors, you can actually like see those contacts. So we know we are measuring the regolith charging. It's just the door never actually opened. So we weren't able to like do the measurements that we wanted because it's not going to open if we don't get to the microgravity portion of the flight. But soon, again, for this too, I'll have great data.
So that high voltage enables for your collector plates that you were talking about?
Yeah.
Okay.
Yeah. Yeah. Technically, the door did open right here at the end because triggering things in code, but it was after it landed. So okay, so I'm gonna mostly stop talking, I think. But so these are a couple of examples of experiments that we have ongoing. I think that so a lot of these are in collaboration with folks at different NASA centers. We have a number of other projects I'm working on with DACA and Phil on some plume surface interaction stuff, and with some folks that have small local companies for that. We also have a number of additional projects we're working on developing with folks out at Kennedy Space Center and SwampWorks. And so, yeah, I'm happy to answer any more questions or talk about something I didn't talk about here.
Okay, I go speak with her. And we're open for questions.
I was curious, you were sharing some of the sampling at the beginning of your talk.
Mhm.
So when you sample like that and it disturbs the surface, does
Mhm.
that prevent you from resampling the same location or no?
Yes and no. So you can sample the same location, but you're not sampling the same thing then.
Okay.
So in one of the Japanese missions, I think it was Hayabusa 2, they went back and resampled at the same location. In that case, you're probably sampling stuff that's from lower down than the first stuff you sampled, right? So you can resample at the same location, but you're measuring different things at that point, which is really interesting, but not if you're trying to like resample the same thing.
Interesting. And does it take like a photo of the surface before there's any kind of impact or anything? Like, is the surface before anything's been done recorded?
Yeah. So for ORAX and for Hayabusa, so for both those missions, they did long mapping phases of the objects, of the whole surface of the object before they, and that was both to figure out where they wanted to touch down, but also to get that context, right? And so they used those mapping and all of that touchdown imagery to understand what the surfaces, what they expected the surfaces to be like, and to find somewhere safe to touch down, right? Which was actually surprisingly challenging. And then as they're going down, they are taking imagery the whole way, with several of the instruments. And so just before touchdown, they do have the imagery, and then they took mapping and imaging after touching and disturbing the surface also.
Really
So
interesting.
see how they modified it.
Even if they're going to reposition cameras or add lights to the arms for future missions, because the surface of Ryugu was heavily copied by Hayabusa 2
Yeah,
prior to touchdown, so we have really good images until
right
what,
when you were
2
touching
meters
it.
off the surface or something like that. And
Yeah.
it's like can't see anything now.
Yeah, because so most of the time when you do those missions, you do it where the sun's at your back, so you have the best illumination possible. But then right when the spacecraft is there, it's blocking a lot of the light. Yeah, I don't know how much they've thought about that, or like putting a camera on the end of the sampler or something like that. That would get destroyed things. You have it really determined, I guess.
Where the images right before.
Yeah, it'd be like dart images, where you just like boom, boom, boom. Yeah, I mean, definitely having some sort of like floodlights, right, could help. Or doing it with like a slightly off 180 sun angle, where you are having still the sun reach there a little bit better. Although some of the images with you can see the spacecraft shadow on the surface of Ryugu and Hayabusa, some of those are my favorite images.
I mean, that is cool,
Like,
but you can't do that.
but you can't see. But then later you can't see. Yeah.
You mentioned that you apply an electric field, right? So from the motion of the particles, can you solve for Q? I
That's
think
the
there's two,
idea.
No.
You can solve for Q, right? It's really a function of mass too.
Yeah.
So it's really Q over M.
Yes.
We use a pretty narrow size range of particles, so we can reduce the effect, like we can estimate what M is to solve for Q, is the idea. And we're doing some in-lab testing right now, where instead of having the material fly up, we're sprinkling it down and looking at how it behaves in the electric fields. And so that will hopefully help us narrow down the behavior as well.
You will get an independent estimate of the Q from the plate charge, right? Because they should be conserved.
Yeah, they should be similar. I mean, it's because we're measuring the charge transfer to those different insulating materials, right? There is a little bit of an effect, but we'll be able to measure how much those are charging and get an estimate then for like what sort of the magnitude of the tribocharging is, and be able to apply it to the sort of small grains. Yeah, we're hoping to have this sort of holistic picture. And it's going to be a combination of ground-based, like just sort of how much do we, because you can get the charging in the ground-based data, you just don't get the dynamics.
Yeah.
So it's a combination of sort of ground-based experiments with different versions and then the flight version. Yeah.
I know in a lot of industrial operations with big smokestacks and stuff, they have electrostatic dust collectors.
Mhm.
Has anybody thought about? I never occurred to me, that like in microgravity, you could exploit that to where you could maybe lay something on an asteroid and have charge the particles and just sit up there and collect them instead of trying to
impacting
jam
onto the
well,
surface.
you get the small stuff, I guess.
You might, yeah. I mean, yeah.
I don't know.
No, I haven't seen So there's definitely interest in doing electrostatic dust collection for like lunar applications,
Yeah.
especially like lunar habitats.
Yeah.
Right, and other lunar ISRU applications. I haven't seen as much of it for like collecting from an asteroid, but it's. You could think
I
of
was curious.
Yeah.
Seems like
interesting.
it's pretty impressive.
It would be interesting to like use some of like the CI simulant
Right.
in one of our drop tower
Yeah.
experiment. Well, you'd need a longer duration, but with an electric field and see like if it, how much you have to charge it before it moves.
Right.
It's like in the lab on campus, I have an electron gun, right? So I could
Yeah.
put a bunch of electrons on some grains and see how high you have to get the charge, how high you can get the charging, and then how high you have to get it before stuff really moves around.
I mean, it'd be interesting just to even between two plates, have the regolith on one of them and
Yeah. We've-
charge up in microgravity and
So
see
you can
how much
definitely-
actually.
Yeah, so you can definitely get levitation and lofting of
Right.
grains, moving between things depending on what that electric field is. Yeah, there's some folks who built little small scale versions of that.
Okay, any questions from online? Please unmute yourself. There's a comment there from Lucia. I think that's to add in the comment. So Lisa says, I'm working on fast motors and the electrostatic forces that are of interest as well regarding their cohesion.
So fast rotating asteroids, I think. That's what. Yeah, for fast rotating asteroids, understanding how they stick, how those particles stick together and how they're one body. Something you have to have pretty strong cohesive forces. So there are questions of if it's mechanical or if there's additional electrostatic forces that help things stick together. Cool.
Okay.
What's the precision of these accelerometers? You can measure up to 10 to the power of -5.
So the station accelerometers are really good. Those definitely have magnitudes of like 10 to the -5, 10 to the -6. The ones we use on our parabolic flights and on our suborbital flights are usually 10 to the -4, 10 to the -5.
What are they?
Hmm?
What sort of sensors are they?
For the ones we do on our flights, they're either just like pre-made little kits. There's one called Yoast, and I forget what the other brand is. And then there are some we bought from like Spark Fun that are just their little IMU accelerometers.
Like MEMS type.
Yeah, they're just MEMS accelerometers. I've looked at much higher quality ones, but have never bought and or used them. Because there are some really nice triple axis ones you can buy that are really sensitive down to like 10 to the -6. They're just also very expensive.
But we also a lot easier to break.
They're
Like, maybe not
probably
as
harder to
easy,
like
but-
calibrate, easier to break. Yeah. I'm really good at breaking.
I mean, we've broken plenty of those, the small ones, but I can't imagine it's easier to break, but.
Some of them are more ruggedized, so.
Yeah. They're probably ITAR controlled too.
Might be.
Okay,
Thanks.
I think we're almost about the time. We have time for maybe one question, so.
Or everybody can get a cookie
All
or
right.
an apple.
All right, let's thank our speaker again. Thank you,
Good
everyone.
question.